All right, so we're going to continue looking at section 7.6. So we went over how to do a quadratic type problem yesterday. This one is very similar, but what do you think you have to do first in this one to make it look more like that? Well, what do you always do when you're solving a quadratic? Yep.
Make it equal to 0.
Make it equal to 0. And when we're trying to solve a quadratic, what did we say about the squared term yesterday? We always want to make sure that it's, yep,
It's not negative.
that it's not negative. So I'm going to put it on the right-hand side. And you might be like, well, wait, that's going to make it negative. Yes, it is. But watch what happens. Okay, so put everything on the right-hand side. It's actually going to save us a step doing it this way. So we subtract it and we get a negative. Now, in order to be a quadratic, what has to happen with the trig functions? They all have to, yep.
They all be the same.
Yeah, it's going to be the same base function. Right now you're mixing a sine with a cosine, so we got to substitute for one of them. Which one did I say we always substitute for? Yep.
Cosine.
Yeah. Well, no, not cosine. Sorry, I got excited. I was hoping we were right. But no, not cosine. No, which one do we always substitute for? Yep.
Cosine.
In this one it's sine, but we have to be a little more general. Yep.
First, I as an exponent.
An exponent of 2, yes. You always substitute for the one that's squared because you have a Pythagorean identity that will get you what you need. What is sine squared when we rewrite that using a Pythagorean identity? Yep.
Is it 1 minus cosine squared?
Yep, 1 minus cosine squared. Now maybe you can see why I made the sine squared negative, because it's not going to be negative when I distribute it. Okay, so distribute out your negative 2 and write it in descending order. So you're going to have positive 2 cosine squared plus cosine x minus 2 plus 1. So I'm going to combine those like terms together. And that's what we get. Any question up to that step? Because now it's a quadratic where the third term is a number, a constant. The middle term has an exponent that's half of the exponent on the first term, and they all have the same base trig function. So that's perfect. That's what you need to have to be a quadratic. What's one way that we can solve a quadratic? And I generally prefer this way if it works. Yep. Yeah, and this one is factorable. Does anybody see how, well, let's just go step by step. What would be the first term in each of my parentheses? What and a what? Yep.
2 cosine x.
2 cosine x
Cosine x.
and a cosine x, just like having a 2x and an x. Same idea. What about your signs? Positives, negatives, or one of each? Yep.
1 of each.
Yep, we need one of each, and it does matter which one we put where. Let's just try plus minus. If it doesn't work, we'll switch it. And then 2 numbers to multiply to give us 1. Is that going to give us cosine x in the middle? Distribute that out. What do you get in the middle? x, not cosine x.
That'd be negative cosine.
That would be negative cosine x. So how do we fix that so we get positive cosine x? Yep.
Make it minus 1 plus 1.
Yeah, so make that a plus, make that a minus. Now when you distribute, everything is good. Okay, so we factored it. What do we do with each factor? Yep.
Set it equal to 0.
Set it equal to 0. When you set the first factor equal to 0, you're going to have to add 1 and divide by 2. When you set the second factor equal to 0, you're going to have to bring the 1 to the other side. So I like to do that just so it saves me the step of isolating the trig function. It's already isolated. All right. 1/2. We should be able to do that one. What angle has an x value of 1/2 on the unit circle? Yep.
30 degrees.
30 has a y value of 1/2. So you're in the right. You're using the right triangle, but just in the wrong spot.
60?
60. Yep. And if you think about your ASTC diagram, what other quadrant is cosine equal to a positive number? You already got this one. Davis?
C.
C. What's the formula in that quadrant? Yeah. Not sure? Oh, yeah.
2 pi minus reference angle.
Yep. And what's let's do, just because we're in degrees right now, what's 360 minus the reference angle?
300.
300? Yep. And the reason I did this all in degrees first is because I knew I was going to get nice answers. Now I'll change them over to radians. What's 60 degrees? Yep.
Pi over 3.
Pi over 3. And what's 300? Oh, Kyle, what's 300?
I don't know.
Well, how do you get from 60 to 300?
Add,
Don't think of it as adding. Think of it as multiplying.
multiply it by 5.
So what would 300 be in radians?
5 pi over 3.
Yep, 5 pi over 3. Okay, so there's our two answers where cosine equals 1/2. And what angle on the unit circle has an x value of -1? There's only one angle. Yep,
Is it 180?
yep, 180. And if you change that to radians?
Is that negative pi?
Well, our answer has to be between, we generally
Pi.
stick between
Pi.
0 and 2 pi.
Pi.
Pi, yeah. Yep. And it said to find all answers in one cycle. Well, we never really wrote down what a cycle is for this problem. But the cycle of sine to an even power is pi over b. And the cycle of cosine to an odd power is 2 pi over b. And b in this case is a 1 on both. So the period of sine squared is pi. The period of cosine is 2 pi. And the least common multiple is 2 pi. That means you want to look between 0 and 2 pi. If you wanted to look in the cycle before, you technically could, but you would have to change these answers to be the cycle before. So I always stick with the first positive cycle, 0 to whatever.
So we have two answers for the cosine x equals 1/2 because there's two quadrants where it's positive.
Right, because this is not on an axis.
Okay.
X equals pi is on an axis. So with the 60, I can take the 60, which looks like this, and I can reflect it into quadrant 4 and have the same x value right there. So there's two different angles, 60 and 300, that each have the same x. But the problem with the pi is there's nothing to reflect. How am I going to draw a triangle out of this?
Okay.
I can't. It's just like a line segment. So when you reflect it, it looks exactly the same, which is why you only get one answer. Okay. So any questions on how we got those three? Yes?
So you said that you can't reflect it. Would you be able to reflect 90 or like 270, or is it?
No, when you get them right on the axis and you reflect it, it stays exactly the same.
Okay.
So like if you're looking for a y value of 1, there is only one value that has that. If you're looking for a y value of -1, that's right there, and that's it. That's the only spot. But when the reference angle is in the quadrant, that's when you have to do all this. This does not apply to angles on an axis, just in a quadrant. All right, so we're not going to write this down. I'm just going to show you. Keep in mind that technically there's an infinite amount of answers when you solve a trig equation. And usually we put plus the period times n to represent them all. We're not going to do that in this section. We are only going to be finding answers between 0 and a number. Okay? We're never going to put plus the period times n. Okay? We've done that before, just not today. Any questions on that? Okay, but it is important to remember that these answers do repeat every cycle. Right, let's try this one. It says find all solutions from 0 to 2 pi. Now, does that look like a quadratic? No, not right yet, but it will. It's going to be exactly the same as the first two, except it's not going to be factored. Does anybody have a guess what I can do first here? And it is a technique we've used before when we work with identities. It's not something new. Yep.
Make them all like the same trig function?
Okay, so we might not be able to get them all the same trig function right away, but the technique is to at least change everything to change it. So say it again, change everything to
the same trig function?
ultimately, but we're going to have to do something first. This is something it was the first trick I taught you with identities.
To sines and cosines?
Change everything to sines and cosines. Okay, at least if we do that first, then eventually we'll be able to get rid of one of those other ones. How could we rewrite tangent? Because that's not sine and cosine. Yep.
Sine x over cosine x.
Yep. Sine x over cosine x. Okay. What could I do with that? Davis?
Both sides by cosine.
Yep. Multiply both sides by cosine. Now is it starting to look like a quadratic? Okay, yeah. You have the trig function squared on one side, not on the other. That's exactly what you just had in the last problem. A trig function squared on one side, not on the other. So now it's just like this problem. Okay. So what would we do next here? Yep.
X equals 0.
Yep. And would you want to put everything on the left or the right?
Subtract the 3 cosine squared x.
Yes. Put everything on the left. We want that cosine squared negative for now because of what happened last time. So negative 3 cosine squared x plus sine x equals 0. All right. And what do we do at this step?
change the cosine squared x into 1 minus sine x squared, sine squared x.
So we're going to use our Pythagorean identity, change the term that's squared. Right? And Sarah, what would I do next there? Well, do you see anything on the left-hand side that could be done out? Not really a property that I taught you, but something you would have learned like in Algebra 1? Yep, we're going to distribute. What would you get if you distribute? Yep, so and I'm just going to combine like terms. Actually, there's nothing to combine. So I'm just going to put it in descending order. 3 sine squared x plus sine x minus 3. Now that I don't think is going to be factorable. You could try, but I've already tried. It doesn't work. So what else can we do if it doesn't factor? Yeah? Yeah, Davis? Sorry. Yeah, we're going to do quadratic formula. A is 3, B is 1, C is negative 3. You're going to do it just like you do quadratic if you just had x's and you didn't have sine x's. All right, so we've got negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so negative 1 plus or minus, what's going to be 1 minus 4 times 3 times negative 3? Yep. 37. And now if you were doing quadratic in Algebra 1, you just say x equals, and there's your two answers. What are we going to put on that left-hand side? It's not x equals.
Sine x equals.
Sine x equals. So now we have to do what to get x? Yep.
Take the inverse sine.
Yep, take the inverse sine. So x equals the inverse sine of negative 1 plus root 37 over 6. And x equals the inverse sine of negative 1 minus root 37 over 6. So now let's think of what kind of number this is. Let's look at the plus first. What kind of number is negative 1 plus root 37 over 6? It would come out to a, yep. Irrational. I'm thinking of something else though that's going to help me with the ASTC chart. Yep.
Positive?
It would be positive. How about negative 1 minus root 37 over 6? What kind of number would that be? Jace, what kind of number would that be?
No clue.
Do you know what question I asked?
No.
Negative 1 minus root 37 over 6. What kind of number would it be?
No clue.
It would be negative. Because it's a negative number minus a negative number is a negative number. Divided by a positive number is a negative. So this comes out positive and it comes out negative, which means you're going to get answers in all 4 quadrants. Because you're looking for where sine is positive, and you're looking for where sine is negative. Okay, so we have all 4. Let's start with this one. Let's do the inverse sine of, and then we'll type all that in. So inverse sine of negative 1 plus root 37. I should probably use parentheses around that. So put the numerator in parentheses, and then close your inverse sign. Okay, so I think they said radians, but I'm going to do degrees just because I'm in degrees right now. So 57.901. Okay, and that's quadrant 1. So 57.901, that's my reference angle for everything. So really, I could just use that now to figure out the rest of the problem, but I'll type this in just to show you. But what do you do to get the answer in quadrant 2 with the 57.901? Yep.
From 180?
Yep, subtract it from 180. All right, so we found our reference angle was 57.9, and then we were subtracting it from 180 because we're looking for an answer in the second quadrant. You don't have to type it in, you can just do second answer, and that's the quickest way to do it. 122.099. Okay, so now try typing the second one in, okay, and watch what happens. Let's go back to inverse sign. Just change it to -1 minus root 37 over 6. Let's see. Okay, it might be, let me check if that's bigger than -1. If it is, remember domain of inverse sine is only -1 to 1. We might not have to do the second part. -1 minus square root of 37. Oh yeah, that's bigger than -1. So because that's outside -1 to 1, there's no solution for this part. So those are your only two answers. If that second part had worked, then I would have gotten 2 more answers. But it didn't, so I don't have to worry about it. Any question why I don't have to worry about that second part? Okay, so always keep that in mind. If you get something that's an error, it could be because you're trying to plug in a number that isn't in the domain. All right. I'm not going to do this one. It's very, very similar to the 3 we've already done. You would want to get everything on one side, and then what would you substitute for it? Which trig function? Cosine squared. Yep. It's always substitute for the one that's squared. All right, let's try this one. This one says to find all solutions from -π/2 to π/2. All right. Any thought what we're going to do first to get this set up to solve? Yes?
Set it equal to 0.
Right, set it equal to 0. So we got to get everything on one side. Let's put everything on the left. So 3 tangent to the 4th x minus secant squared x minus 1 equals 0. Now, does that look like the exact format you need to use a quadratic formula or to factor? Yeah. No, what's wrong?
The power to the 4.
Powers are okay. Powers are good. First exponent is double the second. So we can try to do this like a quadratic equation type of problem. So powers are good. Yeah?
Change everything sines and cosines.
Problem is we have a mixture of different trig functions. We have a tangent and we have a secant. So we've got to fix that. Changing to sines and cosines would be one way, but in this one, what do you think you want to substitute for? What do we always substitute for? How about Dan? What do we always substitute for?
You can substitute tangent into sine over cosine.
Well, that's what Claire had mentioned, but we're not going to. We're going to substitute for what we always substitute for, like in this problem when I asked what do you substitute for, and same with this one. What did we substitute for in this one and that one?
You could do 1 over cosine squared and then substitute cosine.
Okay, so you could try a reciprocal identity. I'll give you a hint. It's going to not really help. So, yep.
Substitute for the tangent?
Did I say to substitute for the thing that's always raised to the 4th power? Second power. I keep saying substitute. What's that?
I thought you said the biggest power.
Nope. Substitute for the thing that is squared. Always substitute for the thing that is squared because you have a Pythagorean identity for it. You don't have a Pythagorean, you don't have an identity for anything to the 4th power that's going to change tangent into secant. But we can change secant into tangent. What's the identity that has secant squared in it? Yep. Pythagorean identity. Because we got to change it to something that has tangent. Changing that to cosine still leaves us with a mixture of different trig functions. Yep. Yeah. Tangent squared plus 1 equals secant squared. So substitute in inside the parentheses, change secant squared to tangent squared plus 1. Now you've got all the same trig function. We're going to combine like terms, and it's going to be a quadratic, which I think will be factorable, and you won't need quadratic formula. So 3 tan to the 4th minus tangent squared minus 1 is minus 2. Okay, and let's try to factor that. Okay, the way you're going to factor that is exactly the same way you would factor this. That's a quadratic type of equation. What would be my first term in each set of parentheses? Yep.
3 tan squared and tangent squared.
Yep, 3 tan squared and tan squared, just like 3x squared and x squared. That's how you do the other one. And then what about your signs? Positives, negatives, or one of each? Yep, one of each. So let's try a minus and a plus. And 2 numbers that multiply to give me 2. No. Let's try that. If you multiply that out, that's perfect. That's 3 tan to the 4th minus 3 tan squared plus 2 tan squared. Minus 3 plus 2, minus 1. So we factored it. Now, what do we do with each factor? Reese, what do I do with each factor? Help us out. How about, set each factor equal to 0. So tan squared x And what would go on the other side? Yeah, negative 2/3. Come back to that. And on the right, well, Kylie, tan squared x would equal 1. What's your first step, regardless of which one you want to solve? You have to do what on both sides?
Take the square root.
Yeah, take the square root. What's going to happen on the left when we try to do that? Okay, so this part would turn into tan x. What would this part turn into?
Root 2 over, or root -2 over 3.
So what would happen when you try to take the square root of that? Yep,
Imaginary?
that's imaginary. So because this comes out imaginary, there's no solution. We're not dealing with imaginary solutions with trig. Right? So this has no solution. But the other part still might. What do you get when you take, this is going to break down into two equations. What happens when you take the square root of both sides? Can someone give me one of the equations?
Tangent x equals 1.
Yep. And the other one?
Tangent x equals -1.
Yep. Okay. So we're looking for where tangent is positive and where it's negative. Well, that's every quadrant. So even though one of these canceled out, we're still going to get 4 answers here. What kind of triangle, anyone remember the unit circle, has values that can come out to 1 when you do the tangent? Yeah?
45.
The 45, 45, 90, yes. It's the only triangle that you can do tangents because the isosceles and the, it's isosceles. So your answer is going to be a 45-degree angle in every quadrant. Because if you take the inverse tangent of 1, if you didn't remember the diagram, inverse tangent of 1, you get 45. That's a first quadrant answer. So you got that. Now tell me the other quadrant tangent is positive in quadrant 3, because it's negative x over negative y, negative root 2 over 2, divided by negative root 2 over 2. That also gives you positive 1. What's my 45-degree angle in quadrant 3? Yeah?
225.
225, yep. Now, when you do inverse tangent of negative 1, you get negative 45, but the reference angle is still 45. This is negative 45 right here. We want to write the answer positive, right? Well, actually, let's see what they want. Oh, no, we don't. They want us to write the answer between negative 90 and 90. So we are going to use negative 45. So you got your reference angle here, here. You got that one. What would be the answer in quadrant 2? So remember, this is 45-degree reference angle. Just tell me what that would be in quadrant 2. Yep.
Negative 135?
Negative 135 would be this one.
Negative 225?
Okay, so now you've got the right answer, you're in the wrong cycle. So you went like this. I need you to go like that.
Oh. Positive 135?
Positive 135. Okay. And if you aren't sure, check it. Type in tangent of 135. Make sure you get negative 1. Type in tangent of negative 45. sure you get -1. And the other two give you +1. Now converting them all. Pi over 4. Negative pi over 4. 5 pi over 4. And yeah, because that's 45 times 5, and this is 45 times 3. So those are all the answers we get, but they specifically said only write the ones between -90 and 90. So now I need to filter them. Which answers here are not between -90 and 90? Yeah.
5 pi over 4 and 2 pi over 4.
Yeah, for whatever reason, they don't want those. They just said to find the answers between -pi over 2 and pi over 2. So that's all we need to find. Okay. Any question on that? All right. Let's try factor by grouping. So factor by grouping is identical to what you do when you do it in algebra. There's no difference. When you have a factor by grouping problem, you're going to have 4 terms. If you only have 3 terms, you shouldn't be trying factor by grouping. It won't work. Does anybody see what you can factor out of the first 2 terms? Irene, what do you think? Okay, what are my first 2 terms? Make sure we know what the terms are. Yep, that's your first term. And what's your second term?
3 cosine x plus 6 cotangent x minus
You gave me the second, third, and fourth.
Oh. 3 cosine x?
That's the second, yes. So looking at the first 2, what do they both have in common?
Cosine.
Cosine x. Yep. So we're going to factor out cosine x. That leaves me with 2 cotangent minus 3. And let's look at the last 2. What do those both have in common? 6 cotangent x and minus 9. Yeah.
Got a 3.
A 3. So I'm just deciding if I want to factor out a 3 or a -3. I want to do what you said. Yeah, let's do a 3. What do you get if you factor a 3 out of the last 2 terms? Yeah.
2 cotangent x minus.
Yep. 2 cotangent x minus 3. Now that's exactly what needs to happen for factor by grouping. What can we factor out of each term now? So we went from 4 terms, now you're down to 2 terms. What do they each have in common? But what do they each have in common?
2 cotangent x minus 3.
Yeah, so factor that out. 2 cotangent x minus 3. And what would that leave me with in the next second parenthesis? Yeah.
Cosine x plus 3.
Cosine x plus 3. All right, so now we've got our 2 factors. And Reese, what do I do with each of those factors now?
Times 0.
And how do you do that? we have to take each factor and set it equal to 0. Yep. So cotangent x equals 3 over 2. And cosine x equals negative 3. Let's start with that second one. What's going to happen when we try to solve cosine x equals negative 3? Why?
Because it's cosine x would never be 3.
Yeah, the cosine of x never hits negative 3. You have to take the inverse cosine of each side, and you're trying to find the inverse cosine of negative 3. That's outside the domain. So there's no solution from that factor. But let's look at the factor on the left. Cotangent x equals 3 over 2. How would we get x by itself there? Yeah?
Inverse cotangent?
You would need inverse cotangent. Well, you don't have that button on the calculator. So we need to do something else besides inverse cotangent. Yeah?
1 over inverse tangent?
Not quite. You're kind of close there. If you know the cotangent is 3 over 2, what else do you know? Yeah?
Tangent is 2 over 3.
Tangent is 2 over 3. That we can work with. Now, what would you do on each side that you do have a button for? Yeah?
Inverse tangent.
Inverse tangent. That is going to be our reference angle. Inverse tangent of 2/3. Second, inverse tangent, 2/3. So that's 33 point, just call it 69. What quadrant is 33.69 in? Yep, quadrant 1. What other quadrant should you be looking for an answer in? Third one, because you're looking for where tangent comes out to a positive. Well, you've got your reference angle. What would you do with the 33 to get an answer in the third quadrant? Add 180 to it. So take 180 plus 33.69, 213.69. And if you're not sure, if it should be 213.69, take the tangent of 213.69 and it should come out to 2/3. If it doesn't, then we did something wrong. But it came out to 2/3. Now, I don't remember if they said radians on it, but if they did, take 213. Well, actually, if they said radians, I would have just put my calculator in radians and done the problem that way. And then whatever I got for the inverse tangent of 2/3, I would have written that down, 0.588. That's the first one. And then I would have added it not to 180, but I would have added it to 8 pi. Yeah, just 2 plus pi. So 0.588 and 3.72, or actually 3.73, if we round off. Okay, any question on that one? So they're always going to work out in some way nice. Like it's either going to be something that factors, something that works with grouping, but there's always going to be a way that it'll work out. That's a good one. What's different about this one? This is different than any problem we've done so far today. Yeah.
The argument is 2x instead of x.
Right, the argument is a 2x. Every problem we've done, the argument has always been an x, 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 x. Now we've got a 2x. Well, 2x would be a problem if we didn't know how to get rid of the 2. But I'm hoping you do. How can we fix sine 2x? Yeah?
Make it a sum.
You could, then you got to do all that. And I want to know what that would be, and we've already done that. But that is basically what you do. I just need to find the answer.
You use like the formula that you gave us, so wouldn't that be 2 sine x cosine x?
Right. Now that we've derived that formula, I don't want you to write it as sine x plus x, and then go back through the whole thing and do the sine sum identity. You know this formula, you can just use that now. Okay? So 2 sine x cosine x equals sine x. What do you think the next step is going to be? And it's the same next step that has been in every problem today. Yeah.
Then it equals 0.
Set it equal to 0. That's always what you're doing. Setting it equal to 0. Okay, so I bring the sine x over. What can I do with that now? And this is also something we've done today. You're never going to have to do anything you haven't really done before. It's just figuring out what is it that we've done before that you need to do. Yep.
Oh, factor.
Yeah, what would you factor out?
Sin x.
Yep, factor out a sine x. That's going to leave you with a 2 cosine minus 1. And Reese, what do we do with that? Set each factor equal to 0. So sine x equals 0. And cosine x equals a half. These are all nice answers. Okay, no decimals. You don't need to do inverse sine and cosine. What angle on the unit circle has a y value of 0? Yeah,
180?
180. Which is the same as, let's just put it in the same cycle.
360?
That's still in a different cycle. We're going to keep all our answers between 0 and 2 pi, not including 2 pi.
I don't know.
0. That angle has a, well,
Is
it's,
it like the same thing?
it is the same thing, but it's in a different cycle. So it's like you could also say, for example, instead of pi, you could say 540. But 540 is, you've added 360 too many times to it. All right, so they specifically want the smallest answers, not the later cycles. So 0 and pi. And what angles between 0 and 360 have an x value of a half? Yep.
30 degrees?
That has a y value of a half. So you right triangle, wrong spot.
60.
60. And if the 60 has it, because that has an x value of a half, then you can reflect it, and that has an x value of a half as well. What angle is down there? Yep.
300.
300, which is, Kyle, what's 300?
5 pi over 2. Or, wait,
Well,
3.
It's 5 times this, which is 3 in the bottom. Yep. So that one, don't need a calculator at all. Any question on that one? Okay, at this point, I've really shown you every trick you can do. Sine 2x equals cosine x. Sine 2x equals sine x. This is almost exactly the same problem. You'd use your double angle identity, bring cosine over, and then you'd factor. But you'd be factoring out a cosine instead of a sine. Anyone want to go through that one? Okay with it? Okay. So, and I think this covers pretty much everything. Now, let's look at, just go back to the first one for a second. Every problem we did today, I had you guys do the full problem, right? Like we started at the very beginning and we got the final answers. Some of the problems in the homework are going to start you at this step. Okay? I think the first like 5 or 6 problems. So they've already done the distributive property, substituted with the Pythagorean, done the factoring for you, and set each factor equal to 0 and isolated the trig. So all you have to do is inverse cosine, and you're done. So that when the problems start you here, it's much faster. Okay. There'll be the next set of questions in the homework are going to start you at this step. Okay. They're going to have already done the setting it equal to 0, the distributive, Pythagorean, and the factor. You just have to take each factor, set it equal to 0, and then solve. So it's still pretty fast when they start you off at this step. And then the last, I think it's only the last 2 or 3 problems, they start you at this step. You've got to do the whole thing. Okay, so even though there's like 15, I think it's 15 questions, the majority of them start you at one of these 2 steps, which is like 75% of the way done the problem. Okay. Any question on that? So that's the homework. And 1 through 6, I think you'll be able to do all of those in under 5 minutes. Those are very, very fast. 7 through 10, they start you with the factoring. And then the last 4 questions, I think, 5 questions, you got to do the whole thing yourself. All right, so we will take a look at that tomorrow.